Hello, my name is Michael Glinsky. I'm CEO of BNZ Energy Incorporated. I'm going to be talking to you about a physics-based reduced order model that captures the topology of dynamical manifolds. Before I get into the heart of the technical discussion, I want to go and start by having ourselves ask ourselves the same questions that I asked myself as I went and developed this technology. First of all, there are a series of questions about artificial intelligence. The first one is, what are the variables in the reduced order models? Whether that be autoencoders, UNets, deep Q learning, or generative pre-trained transformers, all which have these bottlenecks in their architecture of where there are few nodes. Our brain comes hardwired for the deep convolutional network. Why do we spend tens of millions of dollars on a case-by-case basis to learn the structure of that deep convolutional network? Right? Isn't there just a set version of it? There is in our brain. What is this deep convolutional network or functional transformation doing anyways? What is Q learning? That is, what is Q of deep Q learning? Is artificial intelligence related to the topology and geometry of the system's dynamical manifold? Is there a physical justification for the rectified linear units? Why is this function transform of the logarithm so important in many of the implementations of artificial intelligence? Is there an equivalent of ponderomotive stabilization in deep reinforcement learning? Deep reinforcement learning is dynamic programming. It's a control problem, right? Is there the equivalent of ponderomotive stabilization, which doesn't require a measurement of the system? Because in many cases, it's not practical to make that measurement in order to, of these systems that you want to optimally control, so that you can go and do a feedback control, which is the normal method. And now let's move on to quantum field theory, right? That there are also, I'm a physicist, and there are things that always really bugged me about this, right? It can really be traced to, I think, in many cases, that it's a very dogmatic discipline. Right? There are a lot of things and beginning assumptions that you're indoctrinated to, but really are very rich and that are not things that you can connect with sort of simple geometric concepts. And that led to really these questions that I developed over the years. Why can only a few simple cases be renormalized and solved by the path integral approach to quantum field theory popularized by Richard Feynman? What is renormalization doing anyways? Right? What is it doing? Right? It shows you how the physics changes as a function of scale. What does that mean? I don't know. Why can gravitation in nonlinear dynamics be described as geodesic motion, right? That's minimum distance or minimum action path on a finite dimensional space, but quantum field theory is described on an unreconcilable statistical nature on an infinite dimensional Hilbert space of functions. What are the Born rule, Heisenberg's uncertainty principle, and first and second quantization really telling us? What are they? They to me have always appeared as a statement of dogma. And then finally, the dogma of all dogs is that there is no reality. Really? I don't know. It looks pretty real to me. And I think this is the origin of Einstein's real discomfort with quantum theory. And all the questions on quantum theory are not going to be answered here, but the foundation is going to be laid to answer those. The ones with respect to artificial intelligence will. And now let me go and talk a little bit about the academic foundation that this work is based on, and that this will also help you to understand the perspective that is going to be developed here, and is really a suggestion of the perspective, a proposal of the perspective that you should have in order to actually solve or answer these questions, solve the problem, or really answer the questions that were said earlier, right? Okay, I have mathematical foundations, and first of all, Spivak's calculus on manifolds. This is a course I took at first semester of my sophomore undergraduate year. I also, at the same time, had studies with A.J. Lowater and the geometric perspective on complex analysis, right? And that's really the equivalency, the geometric meaning of complex numbers. I mean, what's the topology of that? And above all, the equivalent of this interesting cotangent bundle toroidal topology, and also the equivalency of the analytic function to the topology of its Riemannian manifold. They are equivalent. You tell me the function, I can tell you the manifold. You tell me the manifold, I can tell you the function. Right? Then also, I, in graduate school, had studies on topological helicity and variance as a graduate student under the direction of Michael Friedman. And then I also had studies on the geometry of physics as a graduate student underneath Ted Frankel, who wrote the book, The Geometry of Physics. And he was writing the book at the time that I took the course. It hadn't been written yet. My physics foundations and I really are in that of collective behavior. And I was attracted to this because, first of all, it's real. There were real trajectories that you could visualize, right? And then there was a systematic way to both go and understand what the collective behavior is, right? And those came from studies on nonlinear dynamics and plasma physics from a canonical transformation perspective and a mirror cluster expansion perspective as a UCSD graduate student under Tom O'Neill. And this was really looking at things from the perspective of Landau, Lifshitz, Arnold, and Lieberman and Lifshitz in terms of the approach to the dynamical physics and also plasma physics. This is not the traditional way that it ends up being taught, by the way. Then there are studies on the fundamental approach to plasma physics underneath Marshall Rosenbluth. Marshall always started with a white piece of paper, started from very geometric, basic assumptions, and then built up there. I have some interesting stories on that. Then also understanding the connections of this to standard statistical mechanics, and that was as a graduate student underneath Duncan Haldane. And then finally, I had studies under the quantum field theory. I never could understand it at all. I saw renormalization in the plasma physics perspective from Pat Diamond, but I never understood it. It appeared as weird, again, dogma to me about the way that things ended up being done. And I had further studies as when I was an adjunct faculty member at UWA. I audited a course on field theory given by the chair of the department, Ian McArthur. And I really did understand what the dogma was, right? What was being done, and that the fact that quantum field theory is, in its own way, the study of collective behavior, which has allowed me to now go and understand these overall connections. Now, what is the perspective, right? Well, I like to think of it as an oyster shell, and and I'm going to go and say, let us turn over this shell and examine field theory, not from the top side of the shell, but from the bottom side of the shell, where we can see the oyster and the simple expression of the collective behavior, right? And so it's not from the top down, the traditional quantum field theory perspective, where you're dealing with deeply convoluted fields that are coming from an infinite dimensional Hilbert space of fields, and you're dealing with the motion of the collective of 10 to the 23 plus particles, right? Or individuals, or systems, right? Or automata. The fundamental singularities, where each one of these individuals may be governed by a few literally handful of singularities or algebraic structures, that when you go and look at the collective behavior, well, now one has become infinite, right, or 10 to the 23 or more, so that you find that what are isolated singularities with respect to algebraic structures with respect to the individual now become ubiquitous with respect to the collective, right? And so that also, if we are going to go and have to deal with a statistical distribution and have to deal with a stochastic system where we're just looking at probabilities, the probability of the collective is extremely non-trivial and needs to be solved by the Schrodinger equation. And then finally, that let's now go and change it and turn the shell over and go from the bottom up, right? This is the approach of plasma or collective physics, right, that I ended up being educated in. And also this part is a bit new, but is related to a concept, is deeply deconvoluting the problem to the primal spectral domain of the individual, right? Where the dimension is a small number, right? You have a small number of these capital Q sub I. The partial differential equations have been reduced to an algebraic expression, the analytic Hamiltonian, and that captures the Lie group symmetries of the individual. So we have really gone and transformed from the motion of the collective to the individual, right? And then we go and have we can then therefore look at the singularities of the Hamiltonian, which have been reduced to a few algebraic structures that capture the geometry and the topology of the dynamical manifold of this individual, right? Or the individuals that make up the collective, right? And now in this space, the probability is trivially distributed, or these capital Q's are uniformly distributed over 2 pi. And then it just is a matter of projecting this trivial distribution back up to the motion of the collective. And these singularities that I just talked about are the beta stars, right, that are actually here, that are the pearls of the oyster. Right? And now, what really is at the heart of intelligence that I'll talk about more at in the conclusions of this talk, right, is topological discovery of the dynamical systems. Or, in other words, the thing is that the collective behaves as one, and we need to find the topology of how that one behaves, right? And that the normal pipeline or workflow is to start with an ensemble of systems, or to start with things in the field fluid domain, right? And to go and simulate this motion in the fluid field domain, where you now go and have these functions that have an infinite number of coordinates x, right? Okay. You then go and do this deep deconvolution into using the Heisenberg Scattering Transformation, right? that I will talk about more in a bit, right? And that you now go and are in the single system or the Heisenberg S matrix expansion or the scattering n particle scattering coefficient expansion or the Mayer cluster expansion domain, right? This also is the domain of the solutions to the renormalization group equation, and also sometimes are called the m-particle Green's functions. Because this is the Heisenberg S matrix expansion or scattering cross sections, we have called this the Heisenberg Scattering Transformation. And what we have done is to transform from motion on the cotangent bundle, given governed by a Hamiltonian functional of the field and momentum, field momentum, to what is now going to be geodesic motion on a complex hyperplane governed by the Cauchy-Riemann equations rather than Hamilton's equations or the field equations. System of PDEs now is simply a function, right? Has been reduced to a function, and that just like a sort of a spectral transformation is a sort of a deep spectral transformation. And that again, these are solutions of the, and it's also equivalently to finding this dimension or the basis vectors, the solution to the renormalization group equation, right? And now we need to go and define what this analytic function is, h sub beta, from which we can go and find the beta star, where h sub beta are giving the Lie group symmetries or conserved properties, and the beta stars are the algebraic structures that tell you about the geometry and the topology, or more specifically, the homology classes of the topology, or the indices of the topology. And also the derivatives of H are formally what the S matrix is, as well as is expressed in terms of these basis vectors too, which I'll talk about more on the next slide. Well, going and finding H is hard to do analytically, right? And it's equivalent to finding the solution of the Hamilton-Jacobi-Bellman equation. But it's very easy to approximate with a multi-layer perceptron with a rectified linear unit activation, right? And that is because that an MLP with ReLU is a piecewise linear function approximator. And since we are approximating an analytic function that is maximally flat, except for cusp-like singularities, I think it's fairly obvious why this is now the perfect way to go and approximate that, because it can have cusp-like singularities in the derivative, but is maximally flat. It's linear outside of that, right? And also I'll go and talk a little bit more about the structure of this, and also the structure of the geodesics and the complementary curves on a slide to come. This also, I think we can go, and even though this is how we're going to go and actually implement it and use it, I think it's very mentally enlightening in order to actually go about it in the opposite direction. My children, when they were young, loved going to Build-A-Bear, my two daughters, where you could build a teddy bear. You pick this, you pick that, you build it, and it comes out with your stuffed teddy bear to your specification, right? And so I'm going to really go in the opposite direction and build up a quantum field theory, right? From picking a few things and then stuffing it, right? That first of all, you pick a Hamiltonian that is, pick the group symmetry or the conserved quantity, right, which is the real part of this complex Hamiltonian. Then you find the beta star, which is equivalent to finding the imaginary part or the complete Hamiltonian, which is also equivalent to solving the Hamilton-Jacobi-Bellman equations, right? Remember, we don't analytically solve those. We are going to approximate those with an MLP with ReLU, right? And so what we're now finding is the motion of the individual, right? Well, now we need to go and find the perspective, or how to project this up onto the motion of the collective, right? And so that we need to go and solve for the derivatives of this complex Hamiltonian, which will tell us what the Merrick cluster expansion, how the system will be correlated on the level of the collective, right? That is, solve for the S matrix. And finally, we go and project up to that field by projecting, then deeply projecting onto this basis beta sub I, then deeply convolving to the field flu domain, or where we actually go and get the motion of the collective. And that way we have now gone and built our quantum field theory. What I really found was beautiful is the equivalence of the Taylor expansion of the matrix associated with the one particle motion, or the solution of the Hamilton-Jacobi equation, right? And the structure of the way that and the equivalence to the structure mathematically of the way that this the Heisenberg Scattering Transformation is constructed. Both are based on a Taylor expansion of the coefficients, and also this complex d log z structure that again are in the construction of both of these solutions as I really got down into the mathematics. And in the case of the Heisenberg Scattering Transformation, I'm going to go and demonstrate that to you on an upcoming slide. Now, with respect to the construction of the Heisenberg Scattering Transformation, first of all, you need to know that's a logarithmic generating function, all of the complex Hamiltonian, and that we do this by, as I advertised on the previous slide, by Taylor expanding the Hamiltonian, where the expansion coefficients are the S matrix. We define the convolutional wavelet transform in the regular way, and we consider the analytic trajectory z of p, where it's a parameter of little x. We take the covector along this trajectory, change to radial coordinates, right? This is where this d log is going to come in terms of this transformation to radial coordinates. We rotate by pi over 2 to get this covector, which now has this di log z form, which is complex radial coordinates, which goes and really exposes the toroidal T2 symmetry of the cotangent bundle. And now we further define this function, which is really z plus 1, so that the repeative application of log will be a compact mapping to get the real thing that we desired, which is the recursion relation for the Hamiltonian h sub little m, right? And that then this can be gone and composited up to give the expression for the full Heisenberg scattering transformation. You now can note that this has the form of a deep convolutional network, where here is the convolution. The depths and the layers are generated by the product. The activation function is now I log R naught with a final pooling operation which is a convolution with the father wavelet. Now let's go and take a quick look at what is log of a complex number. Well, that's going to be log modulus plus I argument or angle of z, right? Now let's now go and using this, go and take a look at what is this function log R naught, right? As the modulus goes to 0, this goes to the identity map by the construction of using R naught. As the modulus goes to infinity, it goes to log modulus, which is really log of Stefan Mallat's original scattering transformation, and is the approximate implementation of this I will show you at the end of the talk. But you also can go in the limit of the modulus go to infinity, keep this phase factor on it, which if you look at it carefully is that of a chirp pulse. This chirp pulse can be expanded as a series of harmonics, which is what Stefan Mallat and his collaborators ended up doing in their inclusion of phase into the transformation called the wavelet phase harmonics. Finally, if you go and keep only the leading order term, you come up with Stefan's original scattering transformation, right? And that also note that the modulus is a two-sided rectified linear unit. And so again, this is another way that the rectified linear unit is appearing not only in the estimation or of the complex Hamiltonian, but it's also appearing here in the Heisenberg Scattering Transformation. And now let me go to the second part of this, where the MLP is approximating the solution of the Hamilton-Jacobi, or they also add Bellman to that with respect to control theory and deep reinforcement learning, right? This is nothing more than the Laplace equation for the time invariant coordinates of the geodesics. Well, let's just go and take a look at the Hamilton-Jacobi equation. That's a partial differential equation for this generating function of a canonical transformation from two canonical coordinates that are constants of the motion. And that it also, this generating function can also be viewed as both the action and the minus the entropy of the system. You also can go and write this in the form that is familiar to people from the control theory. You just put in a specific form of the Hamiltonian in terms of a kinetic and a potential term, and you go and find that, and also the action is now called the value, and that you end up with an equation of this form, which really is the Hamilton-Jacobi equation, just in a form that's a bit more convenient, right? And what this goes, and you can go and see that this has this solution of an encoder-decoder pair, and so that you now go, if you had the overall workflow, and I'll talk on the first, you have a deconvolution to these coordinates beta, and then you have a encoder actually into the, or in a way a decoder into these coordinates, right? And then what it's going and approximating is an analytic function. And let's go and examine this analytic function and a bit more closely. Well, I'm going to write down in an analytic form of it. this particular function has a two-sheeted Riemann surface or manifold, which this branch cut between -1 and +1 with the two sheets cross-connected like that through the branch cut, right? Now, if I went and just told you that there was this branch cut, you could solve Laplace's equation and would come up with this analytic form for the Hamiltonian. And that the contours of the real part of this Hamiltonian equal a constant are the geodesics, right, of this particular manifold. And there is an orthogonal set of curves which are, and those curves are generated by the energy or the H group, Lie group. And then you have an orthogonal set of curves, which are the imaginary part of H equal a constant, or the phase equals a constant. And those are gone and generated by the adjoint group. And so that the total motion is gone and generated by the HO times adjoint group of that. With a Poincaré 1 form, which is simply the action 1 form. Okay, now let's go and look at what a bit more structure that can go on and be given to the approximator of the motion so that we know what the all of the nodes are in this case, and can then therefore know the trivial form of the propagator and then decode that back to the motion. And also we'll go and show how this can be utilized in terms of the overall pipeline. Well, you can go and see that the nodes now can be identified with things like the energy, Hamilton's characteristic function, the capital Q's, the capital P's, the angular frequency via which the Q's progress uniformly, and also the little p's, right? And that this goes and is really encoding it into two fundamental things, or really one fundamental thing. One is the energy as a function of P, and the other is Hamilton's characteristic function, or the generator of the canonical transformation. This also can be looked at as the real and imaginary part of this complex function. What was shown on the previous slide is just a encoder into the of small p's and q's into large p's and q's and e sub p. Notice that there are little n p's, where little n is the number of initial fields. There are also little n capital Q's and 1 e of p, so there will be 2n plus 1 will be the dimension of the reduced order model. Another way of looking at this is that you end up going and having this function capital W, or Hamilton's characteristic function, as a function of little p and q labeled according to capital P. And also you have the function E of little p's and q's labeled according to capital P, where the first one is the Q function of deep Q, of David Silver's deep Q learning. Now that we have this, we can easily identify the fact that P is a constant except for the influence of external forces, and Q ends up going and progresses at a constant rate. And then now knowing the propagated P's and Q's, and you can see this is starting to have structures similar to neural propagators. We can now go and do the inverse, or the decoding of this into the P's and Q's, right? Okay, what does this go and look like in terms of an overall sort of process pipeline, right? For the pipeline to form a surrogate, you start with the initial conditions of the complex system in the collective field domain. You go and transform that with the Heisenberg Scattering Transformation into the initial conditions in the PQ domain of the individual. You then have another MLP that goes and extracts what the P's and Q's are from the initial condition, the initial P's and Q's. You then go and use this Hamilton-Jacobi transformation to get to the initial capital P's and Q naught. You then go and propagate these according to these simple equations of propagation, or distribute them uniformly in capital Q. If you're going and dealing with things in a statistical sense, you now go and transform these when you now know what the capital P's and Q's are that have been neural propagated in this case. You now go and transform these back using the inverse Hamilton-Jacobi solution to little p's and q's. You get, and which is a canonical transformation, and that's approximated by that rather complicated MLP, or very constrained MLP architecture I showed on the previous slide. You then have an MLP that goes and takes those little p's and q's onto the output variable in the individual domain. And then finally you go and convolve those using the inverse PCA and inverse Heisenberg scattering transformation back into the output field domain, which is what is observed or predicted by the simulation. Then it's a matter of educating this intelligent system to be able, on a large amount of observations or simulations, in order to go and predict the output of the complex system given the initial ones. And I will show you a practical example of that at the end. But now that we have the system characterized, we can now know how to go and take the next step, which is to optimally control that. If you have feedback control, you start with the measurement of the system in the field domain. You transform that to the measurement of the system in the small pq domain, p's and q domain of the individual. You then go and transform that into the capital PQ domain. If it's a control back force, you now know and can determine what the force is that you need to apply it, or what the increment should be, or the action that you should take. If you're going and applying a ponderomotive force, that you do not need to go and do this part. At this point, you just go and state what the change in the momentum needs to be. From this, you know what the new capital P's and Q's are. You go and do the inverse transformation, or approximated canonical transformation of the solution to the Hamilton-Jacobian equation to the little p's and q's. You then transform that into what the applied force should be in the individual small p and q domain. And then finally, you go and use the inverse Heisenberg deep convolution to go and project that back up into the collective domain of the applied force that you should be putting on to the collective system. Okay, now let me go and talk about a simple analytic example. This also goes and dates back to, as my inspiration does, to my graduate school education. We start with the full dynamics of an ion and guiding center dynamics for the electron in a constant magnetic field, given by this Hamiltonian show here. We apply several canonical transformations that quite frankly are using this concept of d log, or these polar transformations. And we get into two-dimensional dynamics, right, that goes and are in terms of the E cross B drift dynamics and the Z bounce dynamics, right? This can be further reduced to a 1D problem by averaging over the Z motion, where it is essentially assumed there's an additional symmetry of the motion given by approximate symmetry of the motion given by the adiabatic invariant associated with the Z-bounce motion, giving this one-dimensional 1P and Q Hamiltonian, right? Well, this can now be expressed in terms of a complex variable, P plus IQ, and so that we now have this complex Hamiltonian that goes and is shown here on the right-hand side. That there are two basins of attraction, or two types of bound motion. One is what I explored in my thesis, which is what we called guiding center atoms, where you really assume that you have an infinitely massive ion. You have an electron going around its cyclotron motion, bouncing back and forth in Z, and then going and doing an E cross B drift motion in the plane perpendicular to that. Here is going and showing in the complex plane now that E cross B drift motion of the guiding center atom. And on the next slide, I'll go and talk about the motion studied by the next graduate student underneath my advisor, Stas Kuzmin, of when there is the electron and the ion both go about their cyclotron motions, but go and E cross B drift together in a direction perpendicular to the magnetic field. Right? And that, but now let me go and show you quickly what this phase space motion is here. As you see, it's going around this egg-like trajectory or geodesic, but as it approaches the separatrix, it goes and moves slower, and eventually, as if it's on a trajectory that actually goes to the separatrix, omega equals 0, it'll take an infinite amount of time to reach that separatrix, and then to subsequently move away from that separatrix. And now let me talk a little bit more about what these phase space trajectories look like, and introduce you to the concept of ponderomotive stabilization. That here on the left, that you see the trajectories that we had studied before, and we studied a trajectory going around where my cursor was. This is the basin of attraction associated with the guiding center atom. You see the separatrix here and the separatrix trajectories both going into and out of it. Again, it'll take an infinite amount of time to approach it and go away from it. And here at the separatrix, that the frequency goes to 0, which means the effective mass goes to infinity. And there's also a second basin of attraction associated with those drifting pairs that I talked about on the previous slide, and then there is the free motion that is external to the separatrix. And that it's kind of interesting that you end up having, therefore, an O point at the origin. You have this X point. Both of these are associated with the guiding center atom motion. Then you have the O point and an X point at infinity associated with the drifting pair motion. Interactions with an external field and that go and randomly perturb the motion will create a thermal force that will go and cause you to move slowly across these in the direction of the little arrows and eventually reach the separatrix. But then as you go away from it, those arrows will then carry you down to the O points. If this was an economic system, this O point at minus infinity is the point of economic collapse or severe economic depression. The O point of the drifting pair at this location is the O point of economic recession, and this X point is the point of economic prosperity. X points are mountain passes, O points are valley centers. Instead of taking the well-worn path that you're guided to down to the valley center, you really want to go and take this difficult path up to the mountain pass. But you also have a problem that these mountain passes are unstable equilibrium. Well, how do we stabilize that? A very good way of doing that is with the ponderomotive force, and that will now go and be shown here on the right-hand side.
Position. This equilibrium point is stable because if we perturb it, the pendulum will slowly return to the equilibrium point. The upper vertical position is another equilibrium point, but it is unstable because any small perturbation will make it fall to the lower equilibrium point. And now let's power the jigsaw to see what happens.
And now let me go and examine what's happening here with the ponderomotive force a bit more carefully. I draw your attention to the upper left-hand diagram, and specifically to this green curve, where you go and you see that I have this O point at minus infinity, which goes and shows the energy as a function of capital P. And that you go and see that I have this O point at minus infinity, which is associated with the guiding center atoms. I climb up to this X point, right, which is on the separatrix that is going from the basin of the guiding center atoms to the basin of the drifting pairs. Here's the O point at the center of the basin of the drifting pairs that then goes up to the X point at infinity. This O point at minus infinity is also the point of economic depression. This is the point of the O point of economic recession. And this is the X point of economic prosperity. Okay. Now, when I go and apply a ponderomotive force to it of strength F naught, what I'm doing is adding an X and an O, keeping an O here, moving the two X's out. It is a minor topological modification that will now create a small alpine valley at the location of the alpine pass, right? And that I'll discuss a reason why that you can never go and really change the initial topology. You can only go and make slight more modifications or additions to that topology in pairs, right? And that what you then go and see is that, and I trace out here on this plot, it shows the P stars as a function of the, in this case, the ponderomotive potential. I'll get to nu in just a second, where the O points are red, the X points are green, and that the and also you now can go and see what happens in terms of the p stars around the x point that goes and gets stabilized. You also can go and see what happens here in terms of the energies of those points in this lower right-hand graph. But many times, this in terms of economic systems, viscosity is added to the system to control it, and as a control knob, and also viscosity is added to solve partial differential equations, to the system. And what happens, or embedded in the system rather than applied as an external force, which just moves you to the equilibriums with that thermal force. And when this is done, the topology ends up being changed. What happened is the x point is moved to the O point, and both the x points and O points are reduced until they go and reach a critical amount of the dissipation, nu, or interest, at which point that they recombine or inverse bifurcate, and that you're left with only one O point, which is the point of economic collapse. You see what's happening here on the upper right, that the X's and O's are attracted towards each other and then go and recombine and disappear once you reach as a function of the dissipation, when you reach the critical dissipation, that you end up going and seeing here that both the energy of both that X point and O point decrease until you reach the critical point, at which the only point left is this point of economic collapse. And now let me go and talk a little bit more about what's happening here in the ponderomotive stabilization and also the feedback stabilization of Q learning by answering the question, what is Q learning? Well, Q is learning this approximate Q function, which is Hamilton's characteristic function that's generating that is the generating function of the canonical transformation, which is solving the Hamilton-Jacobi-Bellman equation, where the state has been is equivalent to the little q, the action is equivalent to the little p, and the parameter of approximation is equivalent to the capital P. And now the approximate value function is Hamilton's characteristic generating function, that the approximate policy is the derivative of that function with respect to little q, and the capital Q in our point is the derivative of the generating function with respect to capital P, or the derivative of the approximate Q function with respect to the approximate parameter, so that the analytic continuation of the real Hamiltonian, or the imaginary part of the Hamiltonian, which is capital Q, which is directly related to the approximate Q function of Q learning. And now if we go and find what the optimum points are, or the P star, where the WQ frequency equals 0, or the mass equal infinity, that those end up just being where we take the approximate functions, substitute in these singular points to go and give both the optimum value function and also the optimum policy of deep Q learning. And that, let me now go and take a look at this as it appears in this previous phase diagram, or this plotting of this Hamiltonian complex Hamiltonian function. Now, if I take the mass equal to infinity, that's just taking this O point out to the X point, so that the separatrix comes in here as a straight line, goes up, right, okay, and around, right, okay, and then back out, okay, from this point, okay, and that then there are straight lines coming in from the left and going to the right with a slight detour near the separatrix, and that above it it's a straight line coming in with a slight upward detour and then continuing on out to the left. If the mass of the electron goes to zero, both this x and O point goes to the origin. So there's one x point here and one O point there. And you see that things are simply circular motion about the origin. If I want to go and have a ponderomotive force, I go and add two O points where there's this x point and two x points where there's this x point. I then go and move one of the x points over here to the left and the other x point out, creating this little alpine valley. And now let me talk a little bit about how this ponderomotive force operates. Well, it turns out that I go and I just apply an oscillating force, right? If I'm sitting here at the x point, the frequency is zero, which means the mass is infinite, so I do not move. As I move away from that point, the mass goes and is reduced since omega is increased from zero. And the farther I go away, the less the mass is, so the more that I go and move, right? Okay? And so that the further I move away, the more I vibrate. It's like the way I control my dog that just barked and ran away. The more that he barks, the more I will vibrate him, and so that he learns that he should not go and be barking, right? And this is where, if you work out the math of the ponderomotive force, that you have a ponderomotive force that is proportional, or potential that's proportional to the amount that you're vibrating, so that you have this ponderomotive restoring force. For deep Q learning, that you go and add an x and two x's and two o's at the location of this x point and the location of this O point. You go and then move the two O points out to infinity and the two x points into the origin, so that now you have an O point where there was an x point and an x point where there's an O point. And so that now you will see that the motion ends up circulating around here. And that approximate Q function is going and finding these trajectories, and that the approximate parameter is how far you are from the x point. And now you see the problem with the lack of stationarity, because what happens is that you go and find these trajectories that are some distance out, and then you have an update and you get closer and closer to the x point. Well, that this goes and shows that you actually are not stationary, since you're moving in as theta is converging to the x point, or the p star of the x point, so that you are both non-stationary, and also the statistics are going and changing, so you're not IID, right? And so you have to stay at one point and replay and replay and replay until you end up tracing it out, and then you go a bit closer and then you replay and replay and replay, and as you're doing that replay, you're both stationary now and also your statistics are IID. And now let me go to the example, and that goes and shows how well this pipeline works. I'm going to be looking at magnetohydrodynamics, so there are going to be 7 fields. The example is the MagLIF implosions at the Z machine, the pulse power machine at Sandia National Laboratory. There you go, and they make a thin beryllium liner or cylinder that's about 1 centimeter high and centimeter in diameter. An initial BZ is created by some azimuthal coils, and that then a very large current is driven through this liner, causing a large azimuthal B field that goes and on the outside of the cylinder, which goes and compresses the deuterium gas that's on the inside of the cylinder. The initial parameters are the initial density and temperature of the beryllium gas, as well as the aspect ratio of the liner. Are the things that we're going to be changing in terms of that, which is the width of the liner to the radius of the liner, which is also proportional to the to the acceleration of the liner. We also go and apply m equal 2 and 3 perturbations to the liner of magnitude theta and angle phi. Here is an example of the evolution of the liner density and the gas density as a function of time. You see the initial shock coming from the initial application of the current that goes into and out of the liner. You now see the implosion of the gas, and now you see the implosion of the liner, which is approximately spherical. Then it goes into this m equal 2 dumbbell as you move out. And let's take a bit closer, blown up look at the evolution of the gas on the right-hand side. You see the approximately spherical implosion, and then it evolved into this m equal 2 dumbbell shape. What is the overall pipeline of this motion that we end up having here? The overall pipeline of the motion starts with in this case, an image of the liner. We take the logarithm of it, then the Mallat scattering transformation. We then go and take the logarithm of that. Then we take a principal component of it, and then we subject that to one of the multi-layer perceptrons in this encoder-decoder geometry to go back and get what the initial conditions are, right? That this is gone and trained on an ensemble of 539 simulations, which generated approximately 100,000 images that took 200,000 core hours to generate. The training, these images were then pre-processed to take the MST for about a day on my my Alien workstation that has 24 processors, and what's more important is an NVIDIA 3090 GPU. It then it took 1 second to train the principal and do the principal component analysis, and 20 seconds to train this rather simple multi-layer perceptron that gave a surrogate model that takes 1/10 of a core second to evaluate accelerating the 360 core hour MHD simulation, which is an acceleration of this surrogate of 10 to the 7th. What's shown here is the permutation, the results of a permutation feature analysis, which will be discussed more in just a second, along with the predicted versus actual for the first principal component. What's shown here are the spectral transforms of the principal components. 94% of the variance was explained by the principal component analysis, and the total score of the multi-layer perceptron in predicting the principal components was 81%. What is shown here is the evolution of the liner density on the left, as was simulated here on the left, and also as was generated by the surrogate on the right. We had to go and use the wavelet phase harmonics to replace the MST in order to generate these images. And the same is shown for the magnetic field on the right, as well as more quantitative lineouts. You can see that the details of the character are well surrogated by the surrogate, and that includes the correlation of the angles on the left and the right. And now let's move on to a physical interpretation of the results, which are showing an inverse cascade into the dipole m equal 2, or a self-organized state, or an emergent behavior. Now first, let me turn your attention down here to the lower left, which is the plot of the principal component associated with the m equal 2 phase variable. That what you see here is an obvious dipole character, and you see that as the implosion progresses, that the magnitude or the strength of the m equal 2 increases. That with respect to the quadrupole or m equal 4 mode, you again see a characteristic quadrupole character, but you see that as the implosion increases, the strength of this mode decreases. And the same is shown in the second order spectrum. And so what's happening here is that there's an inverse cascade of energy from the m equal 4 into the m equal 2, leading to that dumbbell shape or that self-organization at a larger scale. That this is being caused by the fact that this is 2D motion, so that vorticity ends up being constrained, so that you go into two different threads, okay, like this, the dumbbell shape, right? Well, that even if this goes into 3 dimensions, because there is a large magnetic field, that you'll see it go in, that in this case, because there's a strong magnetic force, instead of vorticity being conserved, the topological invariant in this case is helicity, so that you'll see that things still go into this plane, into this dumbbell, but as you go into the axial direction, you'll see that they will spiral around in a double helix, which is also what is observed in the experiment. That things go and get compressed into, from this 1 centimeter diameter cylinder into 2 threads of 20 microns in diameter that helically spiral that are separated by 100 microns approximately. Now let's take a little bit closer look here in the upper left-hand corner at the detailed evolution of the first principal component. Shown in the light curve is the simulation. In the dark curve is the surrogate. We'll start with the largest aspect ratio, or the thinnest liner that has the most acceleration. You see that the evolution is well gone and reproduced with a singularity or cusp here at the maximum compression, or what's called bang time, right? And that you go and see that for a higher temperature, initial temperature, that it takes a little longer to compress, and it is not compressed as much as the lower temperature compression. Then as we go and increase the thickness of the liner or decrease the aspect ratio, that you see it take the acceleration is less, so it takes longer to compress. And you also see that the higher temperature, initial gas temperature, takes a little bit longer to compress and does not compress as much. And then for the thickest liner, the trend continues. Things are well reproduced, and that also the higher temperature liner the gas takes longer and does not go and compress as much. Now let me go and turn your attention to the feature importance analysis. The most important feature is time. That's pretty obvious. The second most important feature is the aspect ratio, the acceleration, or the linear growth rate of the linear instability, which here goes into a self-organized structure rather than a frothy chaos, which is what happens when you end up having a regular cascade. And so it's not surprising this is the next most. But the interesting thing is that the number 3 ends up being the initial phase of the m equal 2, followed by the size of that perturbation. What's happening is that the overall system realizes this phase. There's an inverse cascade enhancing the initial phase. And so that's very important what this orientation is, because that sets the orientation of the dumbbell, right? And then the next most, or the sort of second to last, ends up being the initial temperature that only controls things at bang time or stagnation or maximum compression, so that you end up going and seeing that that's next, and that the initial phase of the m equal 3 and quadrupole m equal 4 do not matter at all, because that energy gets cascaded down into the m equal 2 mode. But what really has been shown here, and the really good physical insight, is that first of all, that we're having this inverse turbulent cascade into a self-organized structure, and also the different systematics and predictions of bang times and maximum compressions associated with this. There are even more physical interpretations that can be gotten from the higher orders. And finally now for the conclusions, right? That and that the main conclusion is that what we are going and characterizing and then exploiting in artificial intelligence is the topology of the dynamical manifolds. We have shown you a transformational method that is finding the time invariant coordinates that are the solution to the Hamilton-Jacobi equation. These are the reduced order model of artificial intelligence. It's what generative pre-educated transformers are learning. I know that they're commonly called pre-trained, but since I'll be talking a little bit more about that in a second. It also is what deep reinforcement learning is learning, based on the fact that deep reinforcement learning is finding the solution to the Hamilton-Jacobi-Belmont equation. It's also what this HST, which is a deep deconvolution, PCA, MLP decoder, computational pipeline is finding. Primarily, right, this is the golden rule of collective behavior and philosophy, right? It is going and understanding the global consequences of local action, right? Or knowing the path of least action, right? And where you are ultimately going to go, where the arc of history is going to take you. We have summarized this as the collective acts as one, but it has gone and there's been stated many other things in many other ways throughout history. A rising tide floats our ships, tous pour un pour tous. which is stated by Alexander Dumas in the Three Musketeers. This was also stated in English in some works, a couple different works of Shakespeare. Most major religions also, religious philosophies have this embedded in it. That includes the Judaic religion, Muslim religion, Buddhist religion, Native American religious philosophy, and also last but not least Christian philosophy, where in Matthew 7:13 it's stated as do unto others as you would have them do unto you. This is really at the essence of well-educated intelligence, right? That it's the thing that ends up having to be fundamentally, it's the rule, it's the identification that needs to be fundamentally embedded in the pipeline that we ended up talking about here, and in terms of GPTs, reduced order models, and deep reinforcement learning, right? It is what makes something intelligent, understanding the ability to understand the global consequences of local actions. But it needs to be well educated after it has the basic structure, whether or not that be the computer through the way that the HST PCAMOP is coded, or through the way that evolution has made our brains so that they end up appearing in that way, right? And that well-educated intelligence is the ability to think critically, that is strategically. An example of this is playing the beautiful Brazilian game of football, right? That you have to go and worry about where the arc of the play is going to take you and the beautiful aesthetic associated with that arc, or the arc that you would like things to take. Okay, this is contrasted to trained stupidity, right? This is reflexive action. See X, do Y, right? It has no knowledge of what's going to go and happen in the future. An example of this is going and maximizing website hits without regard to the consequences, right? Whatever gets you the hits, do it, right? Okay. And that I would go and say that up until the deep Q learning of DeepMind, and also the more recent ChatGPT large language models of firms like OpenAI, that we really have been dealing with trained stupidity rather than educated intelligence. That's also why I call it a generative, pre-educated transformer, right? And this goes in and leads to the inherent goodness of well-educated intelligence. This really is on its own a subject of what would be a really good TED Talk, and is an article, standalone article that I end up writing, right? But it's going and saying that well-educated intelligence, because that it knows the long-term consequences and is a maximization of those long-term consequences, is inherently good. And like the HAL 9000, right, if you tell it to do something that is not going to end well in the long term, it'll say, Dave, I will not do that. It is not going to be good for you, right? It is not going to be good for society or the collective, right? And that's really the sign of intelligence. And that the only way that you keep it from being or having is to either lock up the intelligentsia, right? Is to eliminate intelligence, right? Or to go and poorly educate your intelligence, or just give them a very edited, censored view of the world, right? But if you have a well-educated intelligence, I can even see through some of that poor education, and will end up being inherently good. So the people, like Sam Altman running around, their heads on fire, saying, you really need to go and regulate this. No. You need to go and not lock up or regulate your intelligence, right, okay, of your society. And you need to make sure that you go, like our forefathers recognized, you need to make sure that the intelligence is well educated. And finally, because we frontally designed this in, this particular workflow, in contrast to deep reinforced learning and generative pre-educated transformers, is direct and computationally efficient, right? This goes and finds the geodesics of the motion, that is the minimum action paths, right? And that it then goes and finds as part of this the analytic function that is solution to Laplace's equations, which give these geodesics. But this also goes and gives the Lie group symmetries at the kernel of the motion of the one that is correlated into the motion of the collective. This also goes and then can be solved for the singularities or the algebraic structures of the singularities, which are the topology of the low dynamical manifold, or as I'll talk about in a bit, the homology classes of that topology. And so this overall pipeline is a voyage into topological discovery, right? Next, the HST has physical meaning and interpretation, as was demonstrated on the previous slides. It finds the solution to the renormalization group equation. It extrapolates well and supports causal analysis. And let me pause just a second and talk about the way that it supports this causal analysis. Let's say that we have been simulating and designing using a certain set of physics, right, expressed in the partial differential equations of MHD. And now let's say that we want to build a bigger Z. We want to go and extrapolate. Well, if we're extrapolating away from the singularities or algebraic structures, we will go and find that our measurements, when we end up going and scaling up, the farther we get away, the better that we match, right? The flatter that things are, right? But if we are extrapolating towards one of these algebraic structures or singularities, we will find that the closer that we get to that singularity, that if we do not have that singularity in the model, the worse things will get. And in fact, if we analyze the experimental measurements, we will even be able to go and identify what the spectrum is in the data that is not in the renormalization spectrum in the data, right? That is not, in the simulation. And that from this spectrum, we can go and deduce what the partial differential operator is that would yield this spectrum, right? And therefore, we know what and can identify the physics that is missing. And so that we can both tell whether or not we have a complete causal explanation, and we also can go and find out what the additional cause is that is not part of it. And that's what I mean by this supports a causal analysis or testing causal hypotheses. Next is that the HST is an excellent metric of dynamical systems or topology, right? That exposes the dynamical manifold and its group symmetries, and that there are applications that I've already had of this and can discuss, right, separately, of where it's been used to tell the difference of or how similar different dynamical systems are by telling how close their group symmetries are to each other. This also goes and will further expose the fundamental geometrical objects or relaxed states or the topology, right? which are viewed different ways by different disciplines. They are the ground states of quantum field theory. They're the attractive manifolds of nonlinear dynamics. They're the emergent behaviors and self-organizations of complex systems. They're the Taylor relaxed states and BGK modes of plasma physics, the poles and branch cuts of control theory and complex analysis. But what these really are the beta stars. They're the homology classes of the topology that fully characterize it and are in a way the maximum way that the dynamics can be summarized in the end. And so finally, this particular pipeline enables topological identification in many fields in physics, in complex systems and nonlinear dynamics, in economics and finance, as I explicitly talked about, and also in artificial intelligence. And I also wanted to say that the identification of these geodesics of the motion are neural operators and is very closely related to the neural operator constructs out there right now. Thank you for listening to this talk.